So, good morning. I'm Leonardo Custode, and I'm here to present our paper called A Greedy Iterative Layered Framework for Training Feed-Forward Neural Networks, made by me, Ciro, Tecce, Illya, Bakurov, Mauro, Castelli, Della, Cioppa, and Leonardo Vanneschi. Here is the outline of my presentation. First of all, I will make a short recap of the existing training algorithms, showing their pros and their cons. I will talk about backpropagation and nature-inspired algorithms. Then I will present the proposed approach, which is called GILT, that stands for Greedy Iterative Layered Training. And then I will show the experimental findings, and finally, I will draw the conclusion and list future work. Let's start with the existing training algorithms, more specifically with the backpropagation. Backpropagation has several pros. The most important is that it quickly converges to a local optima. However, it has some cons, like the fact that we have to compute the gradients, and this is a heavy operation, and also that in deep neural network, the two phenomena can happen that can make the training process ineffective. These phenomena are the exploding and vanishing gradients. We have exploding gradients when the magnitude of the gradients is so high that it results in destructive updates to the network, while we have vanishing gradients, as we can see in this picture, when going away from the output layer, the magnitude of the gradients is so low that it results in null updates to the neural network, and so the neural network does not learn. Finally, backpropagation requires us to use only differentiable activation and loss functions that can be a limitation in several cases. Let's switch to the nature-inspired algorithms. Nature-inspired algorithms have the following pros. They are gradient-free, so we don't have to compute the gradients. They usually are less prone to local optima, especially the ones based on populations. And they allow us to use non-differentiable components like non-differentiable activation functions and non-differentiable fitness functions. However, they have some cons, and the most important is that they may be not effective in huge and deceptive search spaces, especially the ones of the neural networks. So, what are the goals of our approach? The goals of our approach are to use gradient-free algorithms to have quick convergence to a good local optima and having efficiency in huge search spaces. So how do we do that? We simply reduce the size of the search space, and we do that by splitting the network in layers and optimizing each layer separately. When optimizing one layer, the other layers are kept frozen, so we cannot modify the weights of the other layers. We start from the first hidden layer and we go to the output layer. Then we can decide to perform another iteration, which we call epoch. Here we have an example of how it works. Here we have a neural network of 3 input nodes, 2 hidden layers with 4 nodes each, and 2 output nodes. In the first step, what we do is optimizing the first set of connection that now is shown in red. Then, after optimizing this layer, we move to the second layer, and note that now the first layer is white again, so it's not being optimized. We do so until we reach the output layer, and after optimizing the output layer, we check for a stopping criterion. If it is met, we stop the training, else we can start another epoch from the first hidden layer. When we repeat a training for an epoch, we use the previous population for each layer to seed the population. So let's see the experimental findings. First, I show you the setup. The algorithms we wanted to compare are backpropagation, also called BP in the next slides, particle swarm optimization, and GILT using particle swarm optimization as its inner optimizer. We decided to use particle swarm optimization because it's a good trade-off between complexity and efficiency in deceptive search spaces, but GILT is extremely general, so we can use any population-based optimizer. The datasets we used are iris, seeds, wine, and Wisconsin breast cancer. We decided to use 4 simple datasets instead of a harder one to have a more thorough assessment of its performance because this is a preliminary work. The network topologies we tested are one hidden layer with 3 neurons, 1 hidden layer with 20 neurons, 2 hidden layers with 30 and 20 neurons, 2 hidden layers with 50 and 30 neurons, and 3 hidden layers with 40 and 30 neurons. The parameters of our algorithm are the following: 15 individuals, 17 iterations, and for the number of epochs, we tested both 2 and 3 epochs, and for each pair dataset topology, we performed 30 runs to statistically assess the results. We also addressed the fairness of the comparison by keeping the budget fixed for all the algorithms. So for the backpropagation, we set the number of epochs like the number of particles times the number of iterations times the number of epochs of GILT times the number of layers. The number of layers is simply the number of hidden layers plus 1. We did the same for PSO by setting the same number of particles and the number of iteration as the number of iteration of guilt times the number of epochs times the number of layers. It's also important to note that the initial weights are kept the same for all the algorithms. That is, for each of the runs, we generate a starting point that is used for all the algorithms in order to compare them as fair as possible. So now I can show you the results. The first metric that I want to show you is the best accuracy on the test set. What we have done here is the following. For each of the 30 runs on a given configuration, we selected the best networks on the validation set and measured their test set accuracy. So what we have done later is counting the number of cases in which an algorithm outperforms all the others. And if we have ties, all the algorithms that have the best test set performance are awarded with 1 point. Here we can see a chart of the best test set accuracy for 2 epochs, and we can see that over 20 cases, backpropagation achieves the maximum in 7 cases, PSO in 10 cases, and guilt in 11 cases. If we increase the number of epochs, the results are even better. In fact, we can see that for 3 epochs, we have that backpropagation scores the maximum in 6 cases, PSO in 9 cases, and guilt in 13 cases. Besides the maximum, we also compared all the runs by performing a statistical analysis with the Alain-Friedman test with the null hypothesis stating that the medians are identical. The confidence level is set to 0.05 and the control method is set as the backpropagation. What emerged is that for PSO, the null hypothesis is rejected, and actually it seems to be worse than backpropagation because it has lower mean and higher variance. On the other hand, for guilt PSO, the null hypothesis cannot be rejected, so there is the chance that it is statistically equivalent to the backpropagation. We also compared the training time, but only between PSO and guilt PSO. We decided to leave out backpropagation mainly for 2 reasons. The first one is that we wanted to assess the speed up given by guilt over the baseline algorithm. And the second one is that the implementation of PSO and guilt PSO are really similar between them, while the implementation of backpropagation is way different, so they cannot be directly compared in training time. What emerged is that guilt seems to be significantly faster than baseline PSO. And we can see it in this chart where we have the train time for Iris. On the x-axis, we have the topology of the network, while in the y-axis, we have the training time. And we can see that for small topologies, the time spent during training is almost the same, but increasing the size of the topology, the time spent by guilt is roughly the half of the time taken by the PSO. We can see similar trends also in seeds, wine, and Wisconsin breast cancer, even though in this last one is not roughly the half, but is still considerably lower. So in conclusion, we presented a novel training algorithm that seems to have quick convergence that allow us to use population-based algorithms, and so their advantages, and it seems to be effective in big search spaces. Last but not least, it's easy to extend, so we can optimize other parameters together with the weights. And future work includes tests on other datasets, because as I said earlier, this is a preliminary work, and now that we know that this is promising, we can test it on other datasets and compare it to the state of the art. Also, we can optimize the process because this is an iterative process, and we start from the first hidden layer and we go to the output layer. And doing so, while evaluating the network, there are redundant computations that are performed. So if we remove this redundant computation, we can further speed up the training process. And finally, since it's easy to extend, we can perform neuroevolution. That's it. Thanks for the attention. And if you have any questions, feel free to ask now or to send me an email.
Okay, Leonardo, thanks a lot for the presentation. So, questions. Leonardo, maybe you can read out the questions and give the answers, or if you prefer, I'll read it.
Okay, but I have to stop the screen sharing to read them.
Okay. Well, maybe I'll read the questions to you.
Yeah, I can stop the share.
Okay, so besides the same initial weights for all the methods, did you use the same random number generation seed? This is a question from Douglas Diaz.
Yes, we set the seed, but besides setting the seed, we also generated the same starting point because we used PSO and guild PSO were implemented by us while we used scikit-learn backpropagation. So the way the initial weights are generated could be different. So we set the random seed and also generated the initial weights.
Okay, okay. More questions? Well, Mark has a very long question. Mark, don't you want to read that out loud?
Yes, can you hear me?
Yes.
Yes, perfectly.
Oh, the first line seems to have been... Okay, anyway, mine is in the small setting that you have here, you could probably try to optimize all the weights at once. So you could check the gain that you obtain in this case. And also there have been some work by OpenAI. It's on reinforcement learning, but you can probably apply it also on classification task. It has been pursued by Ken Stanley and the Uber, now at Uber team, and presented at Gecko last year, I think, optimizing using evolution strategies or all the ways at once with some very specific evolution strategies. So did you compare to this?
No, okay. For the first question, yeah, that's what we did with the PSO, because we had the PSO optimizing all the weights at once, and guild using the same version of PSO to optimize each layer separately. And for the question concerning evolution strategies, yeah, we know that we had we could use a lot of algorithms. Where we just chose the simplest one, which is PSO, but we could use also differential evolution or natural evolution strategies because they are effective as well, but we didn't.
The work by OpenAI optimizes very large neural nets. Wait.
Yeah, I've read it.
Okay, there is another question from Valentino Santucci. He's asking if a different order of scanning the layers during an epoch can bring any benefit.
We thought about that, but we didn't perform such an experiment. But because we thought that it works almost the same way, because in our approach we have that we have an initial starting point that is the configuration of all the weights, and by optimizing each layer separately, what happens is that each layer changes a bit to increase a bit the performance, to converge near towards the nearest local optima. And so maybe, the performance will not be exactly the same, but the inner working wouldn't be so different, I think.
Okay. Any more questions? So one question from Nuno Lourenço. How easily can your method be adapted to use TensorFlow?
It's actually simple because we just have to implement a wrapper for TensorFlow to give us the weights and to return the weights of the network and to set the weights of the network. So we can simply use an ask and tell interface where we take the current weights of the network, we optimize them, and we set the weights of the network again. Okay,
so sounds good.
I was trying to write, but it takes a long time. My question, if you don't mind adding a follow-up, Penousal.
Yeah, sure.
Is how easily could you, for instance, make an optimizer to be included in the TensorFlow tools so your method can be used as a training mechanism for networks? So, for instance, instead of using ADAM or backpropagation or stochastic gradient descent, I can use this method. That was more into what I was asking about.
Okay, I got it. Actually, I used TensorFlow, but not this deeply, so I don't know actually how easy it's to implement, but I think that we can implement a kind of mechanism that avoid using gradients and perform this kind of training on the network. But I can tell you how hard it is at the moment because I'm not this into TensorFlow.
Okay, so any more questions? No? Okay, I guess that's all. Let's thank all our speakers again, especially Leonardo, the last one.